Okay, hello everyone. I just wanted to go through a brief discussion of boundary conditions. And then with the addition of this, I think we basically have enough to, at the very least, start simulations. Because we'll have talked about geometry, briefly about how you need to move the geometry to a region, how we mesh the region, and if we set up boundary conditions, then we should really have all we need to start a simulation. So when we move a part to a region, and actually I'm just going to go ahead and delete this existing region so we can see this again. And I'm also going to delete all of these scenes so we can recreate them. Um, if we have the definition of the thing we want to simulate, the air or the fluid around the object of interest, or through the object of interest in the case of a enclosed volume like a nozzle. We would right click and say assign parts to region. And as a good default, I generally say create a region for each part and create a boundary for each part's surface. There are reasons to select other things, but that's basically what we're going to use all the time for the purposes of this class, since this is an intro to CFD. So we select the part that we wish to move to a region or create a region with. In this case, it's our 2D domain. So we're going to hit apply, which will create that region. We can hit close. And it has created a region. And it has created a region. So if we go ahead and just tell it to run our mesh again, it'll remesh and put a mesh on that region. We talked about the mesh in a previous video. If we wish to see what this mesh looks like, we can go create a new scene. So down to the scene folder, right click, new scene, mesh, and we'll see what the mesh looks like. So when we set up boundary conditions, inside of this region, there's a folder called boundaries. This is a very important folder that you will be doing a lot in. You'll notice there is a boundary for each of the surfaces in this simulation. All boundaries, by default, are adiabatic walls. It will not allow heat flow through the wall. It will not allow fluid flow through the wall. If we just simulated this right now, it would mostly just sit there and do very uninteresting things. Let's go ahead and I'll actually save that for a little bit. Actually, no, we will do this now. So if we want to see what the flow is doing, a reasonable way of doing that is looking at the velocity magnitude and seeing how the velocity changes over the simulation domain. So to do this, we're going to make a new scene. So scenes, right click, new scene, scalar. Since the magnitude of velocity is a scalar quantity. Velocity is a vector quantity, but the magnitude of velocity is scalar. So we can scroll through this long list of things, or actually, if we see it created a new scalar scene, it creates by default an outline, which is the outline of the parts in question of the region, and it creates a scalar scene, or a scalar displayer, I should say. And this is the scalar displayer, scalar 1, is what we actually use. Interesting. Why does this? Sorry, in the recording, everything, a lot of things are showing up black when they really shouldn't be. But I think you still get the point. Um, Scalar 1 is the thing we use to actually show us a scalar quantity. So under parts, it will show us a scalar quantity on the 2D domain. under scalar field, we tell it what function, what thing do we want it to plot. If you click on that, it'll pop up this dialog box, or it should, and we can select from any of a bazillion different things: absolute pressure, centroid, chevron qualities, connected cells, density of the flow, phase index, phase quality, a whole bunch of things that relate not just to the flow itself, but also to the mesh and any parameters associated with cells that change from one cell to another, or that even can change from one cell to another. They don't have to change. If we wanted to, we could plot density, even though for a fluid flow like we're modeling here with water, we've told that it's constant density. It's not going to change. But if we plot velocity and we tell it to run the simulation with this little running man icon at the top. Oh, actually, I need to clear the solution first, because I already ran this earlier. Sorry. Now we hit the little running man, and it should start to do stuff. It is simulating, and we can see that it's basically random eddies and currents because there's nothing driving this flow. It looks like a lot's going on, but look at the scale here. It's anywhere from 0 to like less than ½ meter per second. And this scale is probably going to get smaller as it figures out that, yeah, there's actually nothing going on. So these are all walls, and this is just flow interior to this. It's doing absolutely nothing. That's because everything is a wall. There's nothing forcing the flow inside of this to do anything. It's just like literally you put air in a box and left it there. Nothing's going to happen for the most part. So we need to change some of these boundaries to actually simulate the environment we're trying to simulate. To do this, you select the boundary, and if you look under the properties for said boundary, there's a type property at the bottom left, or near the bottom left, wherever your properties window is. This has several different types you can select. Some different types will not be available for certain types of simulations. That's expected. That's fine. So we have several different boundary conditions. Right now, I think we have the outlet selected. So we have a couple of things that would make sense for an outlet. Just outlet is a fairly obvious one, which should just let flow. This is a little bit of a misnomer because the outlet is technically just this little tiny sliver right here, because that sphere wasn't quite the right size. So if we want to actually make this an outlet, we probably need to also tell the surface of the sphere, which is this arc right here, that it's also an outlet. We could also select pressure outlet. Pressure outlet is actually the one I would generally select because it's slightly more well-defined. An outlet will let flow leave. I don't believe it'll let flow enter. Pressure outlet will let flow leave and enter. Ideally, you do not want flow entering through a pressure outlet in most circumstances. However, a pressure outlet is well defined for inflow and outflow. If flow needs to leave through a pressure outlet, it will just leave. If flow needs to enter through a pressure outlet, it will come in with velocity of 0 and a pressure equal to whatever pressure you tell it under physics values, and with whatever turbulence you specify. Usually pressure 0 and the default turbulence values are fine for a pressure outlet. You generally don't have very much flow coming back in through a pressure outlet, or at least you shouldn't. For walls, we probably just want to leave these as walls. However, there are a couple of other things that make sense to talk about. We also have a symmetry plane. If we didn't want to simulate an entire thing, we only wanted to simulate half of a thing, we could do that with a symmetry plane. All the symmetry plane says is that it acts like the flow on the opposite side of this boundary is doing the exact same thing as the cell on the near side. The flow is symmetric about this boundary. This is actually pretty reasonably defined and very useful for only simulating half of a thing. For example, you only want to simulate half of an aircraft with that zero side slip angle, or half of a lot of things. As long as you know the flow should be symmetric about some axis or plane, you can use a symmetry plane. Symmetry plane doesn't really apply to the simulation, so we're going to leave it alone for the moment. However, at the inlet, we have a lot more to discuss. What are the types of inlet conditions? What are the types of inlet boundary conditions that we have? Clearly, if flow's coming in, this is not going to be a wall. That doesn't make any sense. We have several choices, though. We have mass flow inlet. We can specify how much mass is entering through this inlet. So if we select that for a second, under physics values, we can tell it how much mass is moving through here. How many kilograms, grams, pounds mass per second. Various units like that. And in the case of a constant density flow, you don't have to tell it density. But in the case of a flow that's not constant density, you might have to give it some other values like temperature and pressure that it comes in at. Mass flow rate would be an entirely well-defined inlet for this scenario. Let's actually just run this a little bit. Actually, let me pause this, and we're going to turn up this mass flow rate because this is water. And this inlet's actually pretty big. So we're going to move, let's do 50 kilograms per second. There we go. We can see it slowly starts to converge to a reasonable looking flow field. And then eventually it converges and it just stays the same. I really don't know why parts of this look black. They're yellow to me, but hopefully you can still follow along with what's going on well enough. So that's a mass flow rate inlet. We've told it that 50 kilograms per second are coming through here. And it's figuring out what are the velocities that are necessary to make that happen. Based on areas, which direction the flow is coming in, etc. By default, when you have most inlets, the flow comes in perpendicular to the surface. You can override that if you say, under physics conditions for the boundary, you can tell it, hey, this isn't boundary normal. I want to specify an angle, or I want to specify the components. Or you can also specify some more, some other things a little bit. We're not going to talk about them too much, but it allows you to change how the boundary works somewhat. That's a mass flow rate inlet. We can also do a stagnation inlet. Well, what is this? It says the flow comes in at zero velocity. If in other conditions, you might have to specify temperature as well. But at zero velocity at some total pressure. So let's say we're going to specify this is going to be 1 atmosphere, approximately 1 atmosphere of pressure, 100,000 pascals. I'm going to again. Not the most stable thing in the world. This is moving really fast. But give it some time and it might figure out what's going on. There we go. And it figured out what was going on. Took a little while to get there. About 600 iterations, give or take. but it figured out that, hey, the flow has to enter at about 7.5 meters per second and leave at about 15 to drive that 1 atmosphere pressure differential left to right. This is a stagnation inlet. You also have a velocity inlet, which should not really surprise anyone at all. You specify velocity. In this case, I'm going to say 10 meters per second. About, what is that, 22 miles an hour, give or take? And we can see that velocity comes in at, oh, hey, look, 10 meters per second. And it accelerates to about 20, maybe a shade over 20. Or maybe a shade under 20. It's a little bit hard to tell. Meters per second at the outlet, which is exactly what you expect. You've effectively reduced cross-sectional area by a factor of 2 in this case. There are some other boundaries. You can also mess with the properties of walls. You can act like a wall is moving, for example, but that's kind of a more advanced topic. So to summarize, the basic boundary conditions we have for inlets are mass flow rate inlets, stagnation inlets, and velocity inlets. For mass flow rate inlets, you specify the mass flow rate. For stagnation inlets, you specify the stagnation pressure, sometimes called the total pressure, or otherwise called the total pressure. Or you can have a velocity inlet, where, in a surprise to absolutely no one, you specify the velocity. For outlets, you have a couple of options. You have pressure outlet and just a regular outlet. Usually pressure outlet's going to be the one you want because pressure outlet will let flow come back through it if needed. However, regular outlet is also an option. And then walls are what everything is going to be by default. Now, by default, walls are adiabatic. That is, heat doesn't flow through them. However, we can potentially change that. So I think we told it that this is a constant density flow with it's not even worrying about temperature. I'm going to go a little bit extra here and go ahead and change this for a moment. And we're going to turn on segregated fluid temperature down here. What this is going to do is it's going to say, yes, the density is still constant. We haven't changed that. But it's going to track temperature now. So notice for our velocity inlet, we now get to specify the temperature of the flow. It thinks it's 300 Kelvin. And for walls, there's another couple properties here. You can specify a thermal specification. You can tell it a heat flux coefficient. By default, this wall is adiabatic. We're going to change this to a temperature. We're going to pretend like this wall is 600 Kelvin, over 300 degrees Celsius. And we're going to take a look at a plot of temperature and see where is temperature? There we go. And see what this flow does. So I believe velocity inlet, we're going to turn down the velocity to like 2 meters per second. And initialize this. So right now, everything starts at 300 Kelvin. We tell it to run a little bit. Let's see here. Oh, this is indeed running. That's a pretty subtle difference, though. You can see it is considerably warmer near the walls. Go ahead and stop this from running for a second here. So you can see there is a temperature gradient here. The wall is quite hot, actually, so it's warming up the fluid in question. You can also tell it, hey, instead of a temperature, we can tell it that this is some heat source, that this outputs some number of watts. I'm going to tell it 50 kilowatts. I do not know if this is reasonable or not, but we're going to give it a go and see what it does. Okay, it seems to have figured out that it thinks it knows what's going on here. So let's see here. That's not very hot at all. Let's keep on turning down the velocity to something like 0.5 meters per second. Well, it's still heating up, but not by very much. Turns out water carries a lot of energy. There's a reason they use it for power plants. Um, tell you what we're going to do is we're actually going to change this. Let's see here. We're going to change this to gas instead. It's going to be an ideal gas, segregated fluid temperature. And gravity is going to be a thing. So this should theoretically give us a much more meaningful velocity distribution here. Oh, and suddenly we run into one of those limits where the maximum temperature is limited. Surprise, surprise! Dumping 50 kilowatts into air, which doesn't carry very much heat, actually changes things quite a lot. Let's make this 5 kilowatts. Something a little bit more reasonable. Still kind of crazy, but slightly less crazy. Yeah, it doesn't really look like this is getting particularly much more stable, but the temperature gradient we can still see here. Let's actually, I'm going to try something. Let's flip this around the other way. So we're going to say velocity comes in flow direction is going to be -1. Oh, -1, 0. Flow is going to come in from the right and leave through the left at this point. We'll see if that changes things up any at all. It's going through an expanding nozzle this time. We want it to move through with a velocity of, let's do 5 meters per second. are getting a little bit more of a temperature gradient. You can see here that there's definitely a warm pocket of air downstream of this thing. But point is, that was a little bit off topic. I apologize. The ultimate point is that walls can affect the flow because they can heat or cool the flow depending on your boundary conditions. We won't deal with this a whole lot in this class, but we might deal with it a little bit. So just be aware that by default, walls are adiabatic, no heat flow. In practice, they can indeed have heat flow through them. In reality, most of them will have some amount of heat flow through them. Is it a meaningful amount? That depends on the problem you're solving. Hence, step one, figure out what problem you're solving. Speaking of problem you're solving, at this point, I think we should have pretty much everything we need to start a basic first assignment similar to this one. So, I will be posting that in the near future in all likelihood.